In this video, we present our work, RainyGS, Efficient Rain Synthesis with Physically-Based Gaussian Splatting. We consider the problem of adding dynamic rain effects to open-world scenes in a physically accurate manner, crucial for applications such as gaming, VR, AR, robotics, and auto-driving. However, realistic rain synthesis is highly challenging, as it involves complex, high-order physical and rendering phenomena, like rain streaks, water accumulation, ripples, reflections and refraction, while also requiring high computational efficiency. Traditional graphics pipeline can generate realistic rain effects, but relies on skilled artists to carefully set up high-fidelity scenes. Recently, scene modeling has seen rapid progress. Given multi-view images, NeRF and 3D Gaussian splatting can reconstruct photorealistic scenes. Building on this, climate NeRF and Gaussian splashing combine scene modeling with physics-based weather and fluid simulation, but the former models only static weather, while the latter uses inefficient particle simulation, making both unsuitable for dynamic and efficient rain synthesis. To fill this gap, we propose RainyGS, a physics-based 3D Gaussian splatting simulation framework for realistic rain synthesis in open-world scenes. We integrate high-fidelity and efficient techniques. For rain dynamics, we use shallow water simulation on height maps. This avoids heavy 3D fluid computation and keeps things efficient. For rendering, we integrate screen space ray tracing with 3DGS to create realistic reflections. The result is an efficient, photorealistic, and physically accurate rain simulation with flexible user control. Here's an overview of our pipeline. We start by feeding the multi-view images into PGSR to recover the scene's appearance and geometry. Then, we extract the height maps by rasterizing the reconstructed scene from a top-down orthographic camera. Next, we use shallow water simulation to synthesize dynamic water accumulation and ripples. It's much faster than particle methods because it bypasses complex inner geometry. Finally, we synthesize reflections and refractions using efficient screen-based ray tracing, and blend all these elements to produce dynamic rainy effects. Specifically, we compute screen space reflection by tracing view-reflected rays using depth and normal maps, enabling fast and realistic water reflections. Our screen space reflection achieves similar quality but runs 60 times faster than ray tracing at 30 fps. We show the effects of each element. We add reflections, refraction with Fresnel term, and finally falling raindrops. We evaluate RainyGS on various real-world scenes. On the MIP NeRF 360 garden scene, RainyGS synthesizes realistic rain effects under user-controlled free-view rendering. RainyGS also supports fixed-view synthesis, producing consistent and evolving rainy results across different viewpoints in the same scene. We present more results across different scenes. Here are the light rain with a low water level. The moderate rain with a medium water level. And the heavy rain with a high water level. RainyGS faithfully generates diverse rainy conditions with physically correct dynamics and fine-grained control. RainyGS can also be applied to large-scale driving scenes to synthesize corresponding rainy weather. Helping to create challenging scenarios for testing auto-driving systems under adverse rainy conditions, improving their robustness and safety. We further compare RainyGS with the runway video-to-video generation model. While video generation models often alter scene geometry and produce unrealistic rain, RainyGS preserves the original structure and renders physically accurate, consistent rain effects. Please refer to our project page for more details. Thank you for watching.